Hi there, I'd like to welcome you in our final lecture. In our today's lecture, we're going to cope with verify processes such as spontaneous and induced radiations, operational principles of lasers, mechanisms of nuclear magnetic resonance. Therefore, I want you to focus on our next slide. This is a presentation of large scale of electromagnetic radiations in terms of energy, frequency, and wavelengths. If you remember from Einstein's principles, energy is directly proportional with frequency, inversely proportional with wavelengths. It means the higher frequency, the higher energy is. The longer wavelength, the lower energy is. And correspondingly, frequency and energy both are directed along the same line, but wavelengths depicted along the opposite direction. In upper part of the given scale represents different range of electromagnetic radiations. It starts from extremely high frequency, then terahertz, infrared, which is subdivided into three parts like infrared C, infrared B, infrared A regions, then tiny visible light range and ultraviolet regions. And in upper part of the given schedule, it's given different biological important molecules and different impact of the given following radiations on the given organizations, such as rotations, vibration, excitation, and finally ionization. And in our right column, it's given, this is the schedule table for the precise number of the given radiations, for example, wavelengths, frequency, quantum energy of each radiation is given by number. As you notice from these numbers, one region overlaps with other one in the boundary between two regions. For example, if it's about infrared region, infrared A region, it overlaps with visible light in a region of 700 nanometer. For the both are the same value. It's about overlapping of this region with one another. And if you notice here, two remarkable points is depicted in the picture. One of them and both of them are represented by a red line. The first line corresponds to minimum energy, quantum energy. The second one is about the energy of ionization. And starting from extremely high frequency, which doesn't impact on any biological molecules due to what? In the lowest energy region, the quantum energy is too low to be considered as a possible reason for interaction of this lowest energy with matter. But it increases with frequency. It increases up to vibrational motion of these molecules, up to energy level of this vibrational motion of these molecules, which corresponds to thermal noise. In the first steps, it exceeds this thermal noise, and finally, when it achieves the energy of this ionization, this energy is sufficient for breaking of these covalent bonds within proteins or within other biological important molecules. And due to this, two remarkable points are important, and optimal energy transformation within biological processes occur between two lines, between the minimum, which represents the minimum quantum energy or thermal noise, which is equal to 0.026 electron voltage. And here, and the maximum, it's about the energy of ionization. It corresponds to ionization of water, which is numerically equal to 12 electron volt. And all these optimal transformation occur between two regions. And it included infrared region, which is subdivided into 3 parts, and visible light and ultraviolet region. But for biological organization, this is the visible light, the tiny visible light region is most crucial for extracting of this energy from the sunlight and recovering of this optical information. For these processes, its visible light is important. Now we try to analyze and understand one by one interaction of these all radiations with biological organizations. And in complete form, total these electromagnetic radiations with thermal effect, it's coming from sun. Sun is the biggest source of this electromagnetic radiation, and the second radiation can be taken like heated objects, and also human body, human organism can radiate electromagnetic radiation. But if it's coming like terahertz, starting from terahertz, because the terahertz is important, and infrared radiation which arrives to the Earth's surface, and it may some heating effect on biological organization. But it's not only about the perceiving of this energy, of this quantum energy, because different parts may be sensitive to this radiation. For instance, a rotation of snakes under the infrared radiation in order to hunting of warm blood animals. And this is not about the perceiving of this quantum energy. It's due to only sensitive membrane or sensitive membrane within the skin of these animals with fin hole within the camera of the membrane. Sensitive, but it doesn't perceive, doesn't observe any quantum energy. And it's about the interaction of this electromagnetic wave with the skin of these some animals. And but terahertz radiation, it becomes increasing importance in the last decade, because most of these facilities, manufacturing facilities, which can produce terahertz radiation and also can detect this is terahertz radiation. And this is terahertz radiation. What's so important? Because it's terahertz radiation, it's non-ionizing radiation, and it can be strongly observed by water content of these of the tissues of the human body. Also, terahertz spectroscopy allows us to understand structure of the different biological constitutions. But fatty tissue with lower content of water complicate this terahertz spectroscopy. Conversely, it allows to detect some cancer cells within tissues. For instance, for epithelium tissue, epithelium cancer can be detected by terahertz frequency radiation. And other application of the terahertz in the field of medicine, it's closely associated with dentistry. 3D imagining of teeth, using of different region of this terahertz frequency, it's more accurate, more safer comparing with a conventional X-ray imaging, and it can be widely used in dentistry. This is interaction of this terahertz with matter is based on absorption and scattering of these frequencies. Absorption and scattering, and it leads to vibrational and rotational motion of the molecules within tissue, and different parts, different tissues is sensitive to different frequencies. For example, if it's about infrared region, and vibrational motion may occur under the bigger 10 power 14 Hertz frequency. Above this frequency, infrared radiation may lead to vibrational motion of these molecules. For example, in proteins, which is closely associated with the secondary structure of proteins and with its hydration as well. And this is a vibrational mode of 10 reg 14 corresponds to 3 micrometer wavelengths. Besides, this is vibrational mode only in biological system may occur rotational mode, rotational movement of this organization of these molecules may occur. But this is comparing with this vibrational mode, it may occur only on the several terahertz frequency. And could you feel the difference, terahertz region and this infrared region? And this is so below, so far, so smaller comparing with infrared radiation. I want to repeat, if vibrational mode of the given constitution is about 10 power 14, but rotational mode only corresponds to several terahertz. This is if it's about a movement of proteins, rotational movement of proteins is equal to 1 terahertz. And a vibrational mode also may shift towards the lowest frequency region when it's about collective movement. For example, it's about hundreds of protein molecules, vibrational mode of 100 subdomain, hundreds of protein molecules. This is frequency may shift from the higher to the lowest region. It means under this lowest frequency of this radiation may occur. This is rotational mode, and which can lead to conformational change. It leads to energy changing and conformational change within biological constitution. Either vibrational mode or rotational mode are deduced from linear absorption spectroscopy and linear scattering Raman spectroscopy, and this is both are important. One of them corresponds to infrared radiation, infrared region, other one terahertz radiation, terahertz radiation and terahertz region. Both are crucial, and up to now we have been studying interaction either infrared and terahertz with biological organizations. And the next slide, it's about absorption of the infrared, by water content and by the carbon dioxide molecules. And this experiment was done within the atmosphere layer without any loading of fog and rain, and it was obtained that the maximum absorption of this infrared radiation it lies between 10 reg of 12 and 10 reg of 13. This is peak, the maximum absorption frequency, and the importance of the studying of this infrared and terahertz radiation. It's being widely used by diagnostic purposes in modern medicine. This is terahertz time domain spectroscopy. It opens wide door in diagnostic methods. For example, it gives us, this is time domain spectroscopy. It's about interaction of terahertz pulses with matter, and if sample is illuminated by this pulsing terahertz radiation, it gives us information not only changing of amplitude and phase shift, also can be registered, and this is more complete information we can register comparing with other conventional imagining with single source of frequency. This is massive pulsing terahertz radiation or terahertz time domain spectroscopy. It's more informative and complete information about the structure of the biological organization can be registered by us. And if it's about terahertz and infrared radiation and interaction of this radiation with matter and what's the exposure from these radiations could be obtained, exposure from infrared solar radiation and from the devices, from the facilities which can emit this infrared radiation, and this is more as a preventative measure in the wellness sector. But what about terahertz radiation? It absolutely non-ionized radiation. It's safer, it's accurate, it doesn't damage any tissue, any molecules because of the lowest frequency, the lowest energy. It's more safer and accurate. This is a terahertz frequency region. But what about infrared? If it's about repeated infrared exposure, it may lead to some disorders. For example, burning of skin, it may burn the skin, and also collapsing of circulatory system may occur. But if it's about frequently repeated infrared radiation, it may lead to squamous cells carcinoma, and with combination our source of ultraviolet radiation, and it's more danger. It's about with combination of other ultraviolet radiation. As I mentioned before, it may lead to skin cancer like squamous cells carcinoma. In order to understand the mechanism of this interaction of these radiations with the biological system, we have to pay attention to absorptional processes. Absorption is most crucial processes. And if it's about biological processes, as I mentioned before, as I pointed out before, it lies between 400 for biological processes. It's important the given frequency range, which lies between 400 and 700 nanometers, and which corresponds to quantum energy between 1.77 till 3.09 electron voltage. And as you noted, this is frequency range, this is energies, is far below from energy of ionization, which is danger for this biological constitution, because during the ionization, collapsing or this is destroying of this covalent bond may occur, and this visible light is far below, and this is energy carrying by this visible light is far below from energy of ionization, but it's also above the thermal noise, and the quantum energy is so large isn't sufficient for biological processes, and as you notice, it's above the given number, above the given energy of thermal noise. And how this is photons and the visible light is observed by the biological organizations. In order to understand this mechanism of this absorption, I want you to pay attention to the Jablonski diagram. Jablonski diagram is meshwork of two different energy series, like this is state and triplet state, single and triplet state, the meshwork of the different energy series. And this is ground level. As you noted, this one is first excited single state, the second exciting single state, the first exciting triplet state, the second exciting triplet state. And between this is either single state or triplet state. As you notice here, the energy level, the lowest energy level, which corresponds to heating energy. And what's the difference, principal difference between single state and triplet state? If in single state, pair of electrons have different orientation of spin quantum number. Spins of pair of electrons are orientated in different way, in different direction, but in triplet state they are orientated along the same direction. It means they have two or pair of electrons, both have the same identical spin quantum number, but it's contradicts to Pauli's exclusion principles. And you know, it said that two electrons with identical quantum number never can be located within the same atom. And due to in triplet state, this is other parameters of energy levels of electron must be different. And this is state, and this is state is also termed like degenerative state. And what processes occur during the absorption of these photons? You know, if it's about absorption of these photons from this ground level, and it may excite and comes to the first exciting level, and this is transition from the first exciting level to the ground level, from the first exciting level of single state either, and or from the triplet state. This is two different transitions may occur, and during transition of S1 to S sub naught, it leads to fluorescence, and from triplet state to ground state, it's about phosphorescence. And as you notice, this is time durations are different in both states. It's about during the short time. This is fluorescence occur during the short time. You know, it doesn't need long time, but this one, it takes time. It occurs slowly comparing with transition from the single state. And in order to understand the mechanisms of these absorption processes, this is energy is absorbed by molecules, and it must be distributed between these molecules in order to excite all molecules. And this excitation of these molecules with transformation of these energies from donor to acceptor, you know, it may occur in one way, any way. For example, it may occur by carrying charge. It may occur during the first energy transfer. It may occur different from donor to acceptor, and during the redox processes, which is crucial for us. Now we try to analyze one by one the energy transferring mechanisms of this biological constitution, and take into account that this energy is extracted from the sun and is utilized for very wide processes within biological organization. The first, it's about energy transformation mechanism, which is termed like first resonance transfer mechanisms, and this is energy transfer mechanism occur between the donor of exciting level with acceptor of the ground level. It's about the single transition. During the single transition, this is energy transformation may occur, and I want you to remember one thing. This is single state. It's about the state of pair electron with anti-parallel orientation, and on the other hand, the both electrons have a different sign of spin quantum number. And this is excitation. During the excitation, exciting these donor molecules, they executes oscillation and comes to the ground level. And this is energy is transformed from donor into the acceptor. On the other hand, emission energy is used for excitation of these molecules within ground level, and it requires overlapping of these energy levels, because the smaller frequency difference, the more effectively transformation of energy will be. The next slide also is about mechanism of these processes, like Foster resonance mechanism processes. And as you noted, this is exciting level and donor molecules from the exciting level, and this one is acceptor molecules in ground level. Energy transformation from donor to acceptor, from excited donor to the acceptor may occur. And this is mechanisms, as you notice here, donor emission. It requires overlapping of these donor emission and acceptor excitation levels. If they overlap on one another, then effectively energy transformation may occur. And this is about the Foster resonance transformation mechanism. And the next is about Dexter resonance energy transfer. Dexter energy, in contrast to Foster, the Dexter, it's about transition. It allows transition between triplet states, and it requires the distance smaller than 10 nanometer between the donor and acceptor. And the Foster also, it requires the dipole coupling. This is Foster, but Dexter, it's about between the triplet transitions. This is transition of this energy from donor to acceptor. And the other method, other mechanism of this energy transformation is also about this radiation mechanism. Radiation, it means one molecule radiates and other absorb. Donor radiates, acceptor absorb this, perceive this is energy. And contrast to other, this is following method like Dexter, like Foster mechanisms. This one can be spread over the big distances from molecule to molecule, and it will lead the excitation of big number of these molecules. But this efficiency of this process is lower due to it couldn't be take an important role in biological processes. And the next this is energy transformation, energy which is extracted from sunlight, and the transformation of this energy between these molecules is a due to reduction mechanism. And this is reduction mechanism, it's about the enzymatic processes, and this is where the donor is oxidized and acceptor is reduced. This is a mechanism, it's also so crucial, and it's related to optimal condition. It requires optimal condition between the given compartments. Before the reaction, they must configure in optimal configuration, and it's also about the overlapping of these electron clouds. And due to overlapping, this energy can easily transform from donor to acceptor. And it also requires this specific molecules with this steric structure, and this process is complex. It requires this complex transverse charge. Transverse charge, I mean, here carries charge plays an important role, and between this is carrying charge, the force, electrostatic force, may occur. And all these processes about this distribution of this energy, external energy, between the internal compartments. But the next our slide, it's about inherently emission of this radiation of these photons from the different biological constitutions, and it covers a wide range of these. It covers a wide range of these organizations, starting from these fungi, bacteria, viruses, fungi, bacteria, and animals, and for example, water inhabitants also inherently can radiate. This is photon, this is energy, and during this radiation emission they can be switched, and the specific molecules is responsible for this switching, and during this oxidizing of this luciferin, which is conjunction with luciferase, may emit, this is light, switching light, and it takes an important role, and during some investigational processes in micro and some macro level of these biological constitutions. And different luciferase of these organisms have the different structure, and due to wavelengths of radiated emitted light are different, and also it's due to microenvironments which surround these luciferase, and it can be used for diagnostic purposes like biological luminescence techniques. It is widely being used now for understanding of different structures. And here introduced this switching molecules gives us information about the different structures. Not only this is luciferase like biomolecules, also fluorescent molecules can be introduced to the given constitutions, and switching of these molecules gives us information about the microstructure of the given constitutions. And the discovering of the specific green fluorescent protein, which was awarded with Nobel Prize, from this jellyfish. It's purified from jellyfish from the sea habitants, and this is a green fluorescent protein. It's also important because it can be introduced into most of the DNA, and it gives us information about the processes within DNA, and the other fluorescent molecules also can be used in technology for the diagnostic purposes in a confocal microscope. But this is important also, green fluorescent protein, for understanding of structure of the DNA and different microorganizations. Our next slide is about the other source of electromagnetic radiation, like man-made technology. This is man-made technology is laser. Laser covers a big range of electromagnetic radiation. The full electromagnetic radiation from infrared to ultraviolet. It's also frequency converters. It can convert, this is frequency of the one region of electromagnetic radiation into another one. For instance, By the lasers, infrared radiation can be converted into ultraviolet. Ultraviolet can be converted into infrared. Visible also can be converted into any of them. And this is laser. The word of laser is coming from the abbreviation of these words, from capital letters like light amplification by stimulated emission of radiation. And this places an important role in manufacturing of these lasers, because this is lasers. Manufacturing of lasers is based on amplification of this radiation by stimulated emission. And what's the meaning of these processes? We try to analyze in our next slide. In ordinary, this matters, atoms within the matter, within different states, is a more stable state. It's about the ground state. But when the photon interacts with matter, this is atoms from exciting level can be lifted into from the ground level can be lifted into excited level, and the lifetime of this exciting level is the shortest, approximately 10 degree minus 8 seconds. After this 10 degree minus 8 seconds, this is atom will radiate this radiation and return to the ground level. This kind of radiation emission is termed like spontaneous emission. This is atoms randomly, individually radiates this energy. If it's about any number of these atoms, they will radiate. This is resonance frequency and becomes to the ground level spontaneously, independent of anything. It's radiate, emits, and come to the ground level. But if this is exciting atoms will interact with photon, additionally it will interact with the photon, and a more powerful radiation will be obtained in the resonance frequency. Also they will return to the ground level. This kind of emission is termed like stimulated emission. And what's the difference between spontaneously and stimulated? There is no stimulation. This is atoms absorbed photons energy and comes to the exciting level. Then it radiates itself. This is energy, returns, comes back again to the ground level. This is spontaneously occurred, but this is stimulated emission occur under the interaction of this photon. Photon will interact with this atom and it will radiate this energy. It was studied by Albert Einstein in 1916. Albert Einstein proposed that this photon will interact not only with ground levels atom, it will interact also with exciting atoms, and this is emission of exciting atoms will radiate. This is more powerful energy. This is about stimulated emission. Now next slide we'll discuss about the mechanism of this stimulated radiation. Probability this is distribution of these atoms belongs to Boltzmann distribution, and it means in ground level, in ordinary, this is ground level is more stable, and the number of atoms in ground level is higher, it's bigger than the number of atoms in exciting level. And absorption probability of this absorptional processes is higher
then the probability of these emission processes. These signals will be so weaker because of number of exciting is smaller than the ground level, and here signals, here this is radiation will be attenuated with time, and if we need amplifying of these signals, here in excited level number of atoms must be higher than the ground level. The more atoms within exciting level, the more powerful the radiation will be. And this is processes can be done by the special techniques which can reverse these processes, and then occupying of this exciting level will be obtained, because everything it's about occupying of this exciting level, and this condition is termed like population inversion, because the reverse processes is possible through the special techniques. It means population of this exciting level, or more atoms will be there in exciting level, occupied this is exciting level, then radiation will be more powerful. And this is a formula by mathematical operation. It can be done in our next slide. Probability of this emission and radiation processes is represented in our slide. This is a transition. This is index 1. It represents a designation 1. It represents the first level, ground level. Designation 2, it corresponds to the exciting level. If it's about 1, 2, it represents transition from 1 to 2. On the other word, it will represent absorption processes. First of all, atoms in the ground level would absorb this is energy of photon, and it will come from 1 to the second level, to the exciting level. It will be lifted by this photon from ground to the excited level. But this is designation 2-1, it represents transition from second to the first, to the ground level. Transition can be by spontaneous radiation, and this is capital A, represent the Einstein coefficient for spontaneous radiation. And the second term, it's about stimulated emission, and when the atoms interact with the photon and comes from the exciting level to the ground level. And generally, this is energy, absorptional energy is used for spontaneous and for induced transition. This is transition occurs spontaneously because not all atoms are coming to the ground level by stimulated emission. Some of them randomly will radiate this energy and comes to the ground level. It represents, this is energy, absorptional energy will be used for spontaneous radiation and for induced radiation. With the U here, it represents the spectral density of this radiation. Then here it is found spectral density of radiation will be found by this equation, and this is represent, each of them represent probability of these transitions. Here also it's written absorptional energy is used for what? For spontaneous emission and for induced emission. And if we simplify it by some mathematical operation, it will come to this shape, to this form, which corresponds to Boltzmann distribution. But if we'll compare it with Planck's equation, which is written for absolute black, but for radiation of the absolute black body, you could feel this is similarity of these equations. But when this is equation becomes approach to infinity, or probability of this spectral density of radiation approach to infinity when the absolute temperature approach to infinity. Also, this spectral density will approach to the infinity, and this is requires this is condition where the Einstein coefficients for the absorption and induced radiation must be equal, and this is corresponds to inversion population of this tramping or inversion population, because it's reverse processes. In normally, in ordinary, the number of atoms within ground level is higher than the exciting level, but if we are interested in reversing of these processes, when it's reverted by us, this is condition must be taken into account. The number of atoms within exciting level must be higher than the ground level. But here the final formula, it's about the ratio of spontaneous and emission radiation. This is mathematical mechanism of the given processes. But what about the properties of this laser beam? Unique properties of laser beam, it's about the coherency of this laser beam. Coherency, it means the phase or wave through the bundle of these waves is correlated in space and time. From here it arises directional of this light beam. Directionality, laser light is usually in low divergence. It can be focused into the small area due to its more powerful, and it can be focused into the small area. On the other hand, also monochromaticity must be taken into account. This is monochromatic laser beam. Laser beam is monochromatic. What does it mean? It means if this ordinary light comprises 7 colors, but monochromatic, it included only single wavelengths. Any of them is included into the laser beam. And this confocal microscope utilizes red and infrared electromagnetic wave frequency in order to visualize, in order to get this information about the structure of the buried tissues. And what's the principal difference between this confocal microscope and ordinary microscope? If in ordinary microscope using light beam only is reflected from the back and front part of the sample, and we could lose information about the structure, layer structure of the given sample. But in a confocal microscope, this is only part of this beam is reflected by the sample, and the other part of this light beam will be scattering from the other layers, and elimination of this light from the other layers, it gives us information about the deepest structure of the given sample. And in modern medicine, also other methods like coherence optical tomography. Optical coherence tomography is being used now. The same principle, operational principle, is similar, is closer to confocal microscope, and but resolution of this optical coherence tomography method is smaller comparing with optical confocal microscope. Why? Here, in optical coherence tomography, this is resolution is 10 micrometer, where in confocal microscope it's about only 1 micrometer. This resolution of this confocal microscope is better than the given this optical coherence tomography. But however, this is masked during the penetration of this laser beam into the given sample more deeper comparing with confocal microscope. If in confocal microscope it's less than 1 millimeter, this is penetration of laser beam is smaller than 1 millimeter, but here in optical coherence tomography it's equal to 2 and 3 millimeters, alters between 2 and 3 millimeters. It means it can penetrate deeply and gives us information about the structure of the studying organ. And in the given picture, it's depicted schematically. This is optical coherence tomography. Is depicted on the picture. This is laser beam, and this is laser beam which is belongs to infrared radiation with wavelengths of 800 nanometer. It's part of this laser beam here using this is mirror, partially silvered mirror, which can shade this is laser beam into two parts. One beam will send to the studying organ, studying tissue. Other part of this light laser beam will be focused on other mirror, and this is mirror reflection ray from this mirror will be a reference beam. Reference beam uses in order to provide interference picture during the reflection of this light beam from the given organ, and a reference beam it will interference and it will provide interference pattern, but not multiply. This is reflecting beam will be in correlance with laser beam with reflected light, when reflected from the mirror. Only part of this laser beam will be in corresponding phase relation with the reflected light, and it will give us information interference pattern of this given sample. Information about this part. What part I mean? I mean here the retina, structure of retina can be visualized due to interference of this light beam from this sample. I mean this is a retina structure, and surrounding layers, not only one layer, all layers of the given retina can be detected and analyzed. Structure of these all because of what? Because of different scattering, different reflection from the different layers. It gives us information about the layer structure of the retina, and this is optical coherence tomography, not only being used in ophthalmology, and it's also dermatology in order to understand structure of skin. This is laser beam. It provides interference patterns. And what's the second important thing? And this is position of this second mirror is altered, it's changeable, and changing of this mirror's position, we could take 3D image of the given tissue. 3D image, layer by layer, altering of this position gives us information about the structure of the given retina. Layer by layer, focusing angle will be changed, and correspondingly this is image also will be obtained, and due to optical coherence tomography. And the other scanning technique, like it's also about the infrared scanning device, which can detect the signals from our intracranial cranial part of our brain. It's non-invasive method from the surface of our skin. We can take information about the bleeding intracranial section of our brain. And this is, as you know, it used to do with computer tomography. And computer tomography, and you to taking of our patient to a hospital, it takes time, and this is, if you know, it also diagnostics take time with the computer tomography, and it's expensive. But contrast to this conventional, this is computer tomography, this is device is portable, as you noted, only approximately the size of book. It's portable, easy to take it where we want, and during approximately 2 minutes it can be fixed. Detect this is information about the bleeding within our brain, and also it costs, it's not expensive, it's cheaper comparing with computer tomography. Only 1% of this price it costs. This is the diagnostics with this portable device, which is termed like infrared scanning technique. And what's the operational principle of this method, of this technique? And sending of laser beam can be observed differently by different tissues. You know, it's strongly observed by blood, and comparing with the brain tissue. It's weaker for absorption of brain tissue is weaker than blood. Blood can absorb, this is light beam, laser beam, strongly. And due to intensity of light will change, intensity of the bleeding, it will be lower comparing with the normal tissues, and it will give us information about the bleeding within our brain. Okay, the next important crucial method, you know, in order to understanding of the structure of the biological samples in atomic level, it's about atomic force microscope. Atomic force microscope has the same resolution with the electron microscope, approximately the same resolution. But what's the principal advantage, what's the principal privilege of this atomic force microscope? Atomic force microscope can learn the structure of the biological sample in their inherent structure, in their inherently surrounding water structure, you know, in their viva. But if it's about electron microscope, you know, this is samples can be studied within evacuated chamber. And this is principal advantage of atomic force microscope. Atomic force microscope, it's about the tip, which is made from silicon nitride, and it's attached to the cantilever like spring-like structure. And this is a sample where there is put on the scanner. You know, distance between these cantilever and the sample must be about the 1 nanometer till 10 nanometers. So nearest it should be, this is the sample and this is cantilever. And if this is putting onto the sample, then inherently Coulomb's force occurs between the sample and cantilever with the tip. And Coulomb's force, as you remember, it's about force between the charged particles. And due to attachment, due to attractive force may occur between the sample and cantilever, and it will be bent toward the sample. And when laser beam, sending laser beam will provide information about the structure of this sample, because it will approach, this cantilever will approach to the sample due to this is attractive force, Coulomb's force, and reflecting laser beam from the surface of the cantilever will provide us with information about the structure of the given sample. And this is sample is movable, this is scanner is movable, moving of this sample, and reflection of this laser beam from the different angles, it will give us complete information about the structure of this sample. And as you notice, this picture is produced by atomic force microscope for the bacteria. In atomic level, it is examined for the bacteria. And the next modern technique which I want to show you is about MRI technique. MRI technique also is a less dangerous method among the other diagnostics method, which is based on nuclear magnetic processes. A description of the nuclear magnetic resonance processes is beyond the scope of this lesson, but some principles are easier to explain. Before explanation of these principles, I prefer comparing of these diagnostics method with other methods like X-ray imaging, computer tomography, and ultrasound diagnostics. And what's the privilege of this diagnostic method, and what's the difference? The principal difference of this method, if ultrasound, X-ray, they need source of these waves, either mechanical wave like sonic wave or electromagnetic wave. And this is based, and these methods are based of interaction of the given waves, illuminated waves, and due to interaction, due to reflection, due to scattering of these waves with matter, with studying sample, with organism. However, this method, this is nuclear magnetic resonance technique, it's based on nuclear magnetic momentum or magnetic properties of human body or soft tissues. You know what does magnetic momentum means, and it should be explained in level of atomic level and subatomic level. But each atom comprises, this is constitutions of atom, that it's protons and neutrons, and it's about the even number of these nucleus, then magnetic momentums will cancel out each other. But if it's about the odd number of nucleus, such as proton, such as a hydrogen atom, it possesses magnetic momentum, and changing of behavior and changing of magnetic momentum within magnetic field, it gives us information about the given structure, how it's applicable to our organism. And our organism is about 80% of these water liquids and different solutions. But if it's about water constitutions, which involves hydrogen atom and behavior of this hydrogen atom with a magnetic field, it will be different, and it will give us information about the structure. And due to this method, mainly it's about studying of the soft tissues. Soft tissues, why? Because it involves water, which its constitutions is hydrogen. Everything occurs around this hydrogen atom. Inherently, it possesses randomized magnetic momentum, where the total magnetic momentum is zero. But if we are taking this soft tissue with a magnetic field, or hydrogen, or soft tissue with the water constitution and hydrogen, if we are taking this starting sample with a magnetic field, then what will happen? Then this is magnetic momentum will align parallel and anti-parallel to the external magnetic field. Some nucleus will align parallel to external magnetic field. Some of these nucleus will align anti-parallel to this external magnetic field. And something will happen. Why it's here the more nuclei than this level? Because this level is non-exciting, this is more stable. And I want to repeat again, if we are taking this sample with a magnetic field, first of all, shifting of energy levels may occur and occupying of nucleus in different levels. For example, here, parallel to magnetic field and non-exciting level, it will be more than the higher level. It's not absolutely non-exciting, but it's comparing with this one, this is lowest energy, and this one the higher energy, comparing with this level. And energy shift between two levels is equal to the given ratio, where the B is external applied magnetic field. External applied magnetic field, it alters between 1 and 4 Tesla. Could you imagine if you want to compare this magnetic field with a magnetic field of complete total Earth's magnetic field, which is equal to 10 power minus 4 negative 4 Tesla. You know, magnetic field which is produced by Earth, it's only about, it amounts 10 power negative 4 Tesla. But here, external applied magnetic field, it alters between 1 and 4 Tesla. Could you imagine the huge difference between these? Approximately 10,000 times stronger magnetic field is being used here. And this is energy which is required to lift this nucleus to the excited level, and this is corresponding frequency is termed like Larmor frequency, which also alters 44 and 170 megahertz. It corresponds to the given hertz. And what will happen then? This is nucleus will be lifted to the upper level. Then after certain time it will radiate these they will radiate these signals, which corresponds to the microwave and comes to the ground level. Now we are interested in occupying of this the higher level. It must be occupied by most nucleus due to detecting of powerful signal. And the next slide, it's about how this process takes place. And due to excitation of this nucleus and coming lifting to the exciting level, it needs driving pulse. Driving pulse, it's a pulse generator, and sending of this pulse makes it excited and and this is molecules will be lifted by the external, this is pulse. And when pulse over, then inherently they will radiate this energy and comes to the ground level. And detection of these signals, it gives us information about the structure. And here not only this is nucleus or about the spinning momentum, here different interaction of these spins with each other, with surrounding molecules may occur. Due to detecting signals will be different. And you know, as you notice, this is driving pulse which is used due to excitation of this nucleus. It's like stable, it has this structure. But what about the emitted signals? Emitted signals is damping. I want to compare it with well-made top. For example, during the spinning of top in vacuum, it will be continue for a long time, you know. But if it's within the water solution, spinning of top will be limited. After certain time interval, it will stop. The similar, it's about the structure of this nucleus, because it's surrounded with other nucleus, and this is other nucleus. It resists excitation, resists the sending of these signals, you know, because of the interaction of these spins with surrounding spins. Spins of the surrounding molecules, this signal also will be damped. It also depends on water constitutions. The the more border constitution, the more powerful signal will be. But if it's about the bones, for bones this signal will be damped quickly, and for fat tissue it will be comparing with bone, this signals will be higher comparing with bone, because it needs water constitution. This processes occur within water constitution with hydrogen nucleus. And the next slide, it's about the detecting of the signals of the different experiments, and if two tubes is filled with same water liquids solutions and is placed in uniform magnetic field, where the magnetic field, external field, doesn't change. But here there is no signal will be detected, because the alarm frequency for both tubes will be equal. But if it's about superimposed alternating magnetic field, two tubes will give us different picture, different signals of the Larmor frequency. It also represents different constitutions, different water constitutions of the different soft tissues, and it can be easily detected as three-dimensional imaging by sketch of the whole body. It's depicted on the picture in 3 lines along the 3 x vertical, horizontal, and along the z lines. It gives us complete information about this 3D dimension picture. And also here, what's the advantage of this method? Here, studying tissue, detecting tissue is equal to 0.5 millimeter. I want to underline 0.5 millimeter structure can be visualized during this method. But if we compare it with a conventional CT scan, and for CT scan it's about 2 millimeter. 2 millimeter structure is detected during the computer tomography, but here the smallest, it's about the 0.5 millimeter structure can be examined due to this MRI imaging. And the new modern technique is about functional MRI imaging. It means it allows us to understand functioning of the brain due to different properties of this oxygenated and desoxygenated blood, and different behaviors of this oxygenated and desoxygenated hemoglobin within magnetic field. If it's about desoxygenated blood, it has magnetic momentum, but it's about oxygenated blood doesn't have any magnetic momentum. But for the excitation of the signals for oxygenated blood, it requires high pulse, and it takes time. Excitation of this nucleus within oxygenated blood, then it will radiate these high pulse signals. High pulse signals, it gives us about the oxygenated blood circulation within the given part of the brain. But it's about the weaker signal, because it doesn't require any excitation, because it perceives this is magnetic momentum. For desoxygenated blood, the shortest, the weakest signals could be obtained, and this blood supply of these brain parts can be analyzed, and it also gives us information about different functioning of this brain. You know, if it needs more oxygen, here it will be powerful signal from this diagnostics method. And it also gives us information about different functions, about sensory function, cognitive function of the brain, memory function of the brain. It will give us information. And some disease, it also gives us information beforehand of some disease, like Alzheimer's, Parkinson, and Huntington disease, which is closely associated with brain. As I mentioned before, the topic of our lecture is so complicated, and it's impossible to still them just during the one lecture. It requires days, you know. But our time is over. But if you need my guidance here, you make connection with these numbers, with my mail numbers. Thank you.